Well, hi everyone. It's a pleasure to be able to speak with you here today in this virtual mode. My name is Dave Draper. I'm the Deputy Chief Scientist of NASA from headquarters in Washington, D.C. And today I'd like to tell you about NASA's plans for the future of lunar exploration. And I'm going to start with how we got here. I'm going to tell you about some of the history of lunar exploration, where we've been, what we've observed, how we have learned about the formation and evolution of our moon. We'll find out that there's this thing called the giant impact hypothesis that establishes, as we've come to understand it, really that the moon is the cornerstone of all of planetary science, and we'll see how that happened. And in the last part of the talk, I will outline for you some of the agency's plans with international and commercial partners to return to the moon, to stay in NASA's Artemis program. So let's kick it off. I'm going to start here with a bit of a history slide. This is going to start rolling across the screen to show some of the earliest lunar exploration. This is during the Cold War between the United States and the former Soviet Union, when for many geopolitical reasons these nations were vying for primacy in the space environment after Russia was the first to go to space. And of course, that whole space race era during the 60s resulted in a fleet of robotic spacecraft by the two countries, leading up eventually to the Apollo landings. And of course, we had Apollo 11, 12, 14, 15, 16, and 17 on the lunar surface. Toward the end of that time, the Soviet Union did succeed in landing robotically on the moon in these Luna missions you see here along the bottom of the screen. Those were robotic sample return missions that returned a lot less material than Apollo did, naturally, but they landed in spots that Apollo had not visited. And so over the years since, despite the geopolitical tensions, the scientific communities between the two countries have actually established a healthy sample sharing approach. Okay, here we go. So, of course, during the Apollo era, we had, some of the things about which many of us are familiar. Last year, we celebrated the 50th anniversary of the Apollo 11 landing, which is a huge milestone. Astronauts learned how to live and work on the lunar surface. They did some amazing science on the surface and brought back samples that have taught us how the moon came to be, at least to our level of understanding. We'll talk about that in a second. Here is a photograph of the near side of the moon, showing where the 6 Apollo landing sites ended up. And the primary thing I'm going to focus on today about what we learned from Apollo has to do with the samples that were retrieved by those astronauts. They brought back 382 kilograms, that's 842 pounds of lunar rock and soil. And fundamental questions were immediately answered by these things. For one thing, the moon is very old. It's an ancient body. We now know it's about 4.6 billion years old. We also know the moon moves away from the Earth at about 3 centimeters per year. At earlier times, it was far closer to the moon than it is today, and that has ramifications in a lot of ways that I'm not going to have time to talk about today, but that is a really important concept. The early moon was what we have come to call a magma ocean. It was basically a ball of molten rock that cooled to form the crust, mantle, and core, like you see in this cross-section diagram on this slide. Isotopic compositions of the moon and Earth are almost identical, as we have found from studying these samples, and that definitely favors the giant impact theory, but there are complications, and we'll talk about that a little bit too. We also learned that impact cratering on rocky surfaces is a fundamental geologic process, and that the moon, owing to its lack of an active geologic cycle, as we have here on Earth, is a witness plate, records that early impact history of the solar system. That's important because everything that happened to the moon also happened to Earth, but we don't have evidence anymore. We'll see about how that works. And one more point here is that there was very voluminous volcanic activity on the moon. When you look up at the moon in the sky, you see the light and the dark parts. The dark parts are these lava flows, volcanic eruptions that covered a large portion of the near side, and those took place over several 100 million years in the early history of the moon. All right, here is now sort of the second era of lunar exploration that got going during the 90s. Nothing was happening in between those two things. And here we have a fleet of robotic orbiters mostly from many nations, not just the United States, also from China, from India. And of course, now the People's Republic of China have 2 spacecraft on the lunar surface. I don't have Chang'e 4 on here, but they're out on the far side in the margins of the South Pole Aitken Basin. We're going to talk about that feature in a while, too. Now, here's just a photograph. I mentioned this a second ago. Here you have the near side and the far side. Keep in mind, the moon is what we call tidally locked to Earth. That means the near side is always the near side. It's always facing us. Of course, there is no dark side of the moon. I don't care what Pink Floyd says. The moon, as it orbits Earth, the sun hits all of its surface just like anything else. It just takes the moon a month to rotate on its axis one time, and it's always facing us. So we see these dark areas, and we also can now know that on the far side of the moon, things are very different. As you can see, there's hardly any of the dark stuff. There's not that many lava flows. Instead, there's what we call a highlands crust, heavily cratered, as you can see, and it actually stands up significantly higher, kilometers higher than the basins of the near side. Here's another way to look at the same information. This is topography measured from orbit with using laser altimeters. And what you can see is that the cool colors are low spaces, and the hot colors are the high places. So you can see, again, in the near side, all those basins are low by comparison. But on the right side, here's something that maybe you hadn't noticed before, and it's that really deep purple blob here in the lower part of the diagram. That's a huge impact basin. It's called the South Pole Aitken Basin, as I mentioned a second ago. This is the largest impact basin in the solar system. Full stop. And it's likely to reveal really fundamental secrets about how the moon works once we finally get there. So there's the SPA basin. I also want to show this diagram here of the thickness of the lunar crust. Now this is a similar color scheme, but we're measuring something slightly different here. Now it's not topography up and down, but how thick is the crust in these various places. And you can see right away that there's a lot of similarities, a lot of overlap between those 2 kinds of information. But the thickness of the crust has a lot to do with whether lavas can get out and they might get trapped somewhere in the crust and not make it out. There's a lot of information here that is preserved in the fact that there is this great dichotomy between the lunar near and far side, very unlike what we have here on Earth. We are also able to measure compositions of exposed rock types now from orbit with increasingly sophisticated remote sensing devices. And so this is just an example color-coded for various mineralogies that you might see on the moon. Here's another diagram. This looks like one of the ones we saw before. This outlines how many large basins there are on the moon, all these black circles. And some of them, now highlighted in red, have been studied in detail because we have samples that we think we can that we think came from some of these big basins. And so these help us understand the relative timing of events on the moon. This is the first thing we want to do as planetary geologists, or any geologist. What is the sequence of events? What came first? What came next? That's the geologic history. And the moon helps us with this a great deal in terms of the inner solar system's history. Now, how do we do this? One thing that we quickly understood, and you can tell from all these photographs, the moon has been beat up. There are craters upon craters upon craters upon craters. The uppermost 10 or so meters of the lunar surface has been churned by this incredible bombardment over time. Now, one of the things that we learned when we brought samples back from the moon is that they have ages that we can measure in the laboratory. And if we can confidently assign that rock's age to a particular impact event, we can start to basically develop a calibration curve that if you know how many impacts there are of a given size in a region, you count them up, you can say that surface has been exposed for this long because we have the actual age measurements of the rocks. Now, why is that important? Well, as you may have noticed, just about every solid object in the solar system has craters on it. So some a lot more than others, unlike the gas giants where you can't form a crater in a gas cloud. These rocky bodies also record the impact history where they are. And the cool thing would be is if we could just immediately apply what we learn on the moon to any other body. It's not so simple. The way the impact history went elsewhere in the solar system is different than it was in the inner solar system. We don't actually have samples from any other world where we know precisely where they came from, and so that we can really assign geological significance to their ages for a particular spot. So if we could somehow improve this model, this would be a really important thing to do. And we hope that additional sample returns in the future will help us do that. Because this is the only game in town right now. This is the only way we can try to estimate the surfaces of exposed ages on rocky bodies. And again, that's the most fundamental thing of establishing the geologic history. Okay, we're going to look at this animation now. I'm going to switch gears a little bit. This is now getting into the very most recent scientific findings about what's going on the moon, and it has to do with the poles of the moon. Now, up until the late 2000s, the sample work that was done suggested that the moon was almost devoid of volatile elements like water and other things that we know very well here on Earth and that we know exist on other worlds, for example, Mars. But we thought the moon was so-called bone dry. Well, as technology advanced and we were able to make more and more sensitive, precise measurements, we found out that lo and behold, the moon does have a little bit of water in its materials. And we're talking a vanishingly small amount, parts per millions level. But from the point of view of cosmochemistry, big picture, the difference between zero and not zero is profound. And so we made that change about 10, 12 years ago from thinking the moon was devoid of volatiles to realizing it had some. And that really set loose a new, almost a renaissance in the way we have thought about the moon. Later spacecraft have been able to determine, and we'll see some of this evidence in a second, that there's probably some of these volatiles trapped in the lunar poles where it gets incredibly cold. So let's explore that a little bit. In this animation now, we're going to come up onto the moon, and it's now going to flip over, and we're going to zoom in on the lunar south pole. So here we go. And as we zoom in closer, what's dead center of the view is a crater called Shackleton. And what I want you to notice is, look at these craters. Some of them, the sun never shines. They're always in shadow. Here we go. We're zooming up. And as the sun, we're holding the point of view fixed on the moon while the sun is going around. These are what we call permanently shadowed regions. These are places where the sun don't shine. And they are cold traps. We have orbital measurements of the temperatures of some of these places, and they are some of the coldest places in the solar system, even colder than cloud tops on gas giant planets. On the left-hand side here is a view of the South Pole, which shows the average amount of illumination. So the darker spots mean they get less and less illumination. And you see some of these places never get any. And Shackleton is right next to the crosshairs on this thing. On the right-hand side is these orbital measures of temperature. And again, same kind of thing. Hot colors are warm, cool colors are cold. And what you can see here, just above the crosshairs, is this big purple area where it goes all the way down to like minus 400 degrees. We have craters on the moon where we're only a few degrees above absolute zero. Really surprising finding. And so the thinking is that any volatiles that are in a lunar atmosphere, if it existed early on, we're probably going to migrate to these cold traps. And any other volatile ingress to the moon, perhaps from bombardment from meteoroids or cometary material, is likely to end up in these places. Now, why is that a big deal? Well, we already talked about the cosmochemical ramifications. But to segue into the next part of the talk, it's also a critical resource for exploring the moon. If we can extract this water ice that's there, which is what we think is there, we can help support human life on the surface. We can make rocket fuel. We can do a lot of things that help us stay on the moon in a sustainable way. So here's another look at the North and South Pole. These are measurements of hydrogen ions in these locations. On the left-hand side now, we've got the South Pole area. You can see the Shackleton crater labeled there. And you can see some of these high concentrations in the near polar region. So we have multiple lines of evidence that this is what's happening. Now, what we also know is that the moon's pole has wandered a bit during time. Similar thing happens here on Earth. And the poles where we think they used to be show high concentrations as well. So we don't know exactly when that pole shifted, but while it was near the pole, it helped concentrate some of this stuff. Now you see on the right-hand diagram here, it says L-Cross impact site. There is a mission, or was a mission, called L-Cross, Lunar, I can't remember what it stands for, I'm sorry. And what we did there was we did a bunch of measurements from orbit, and then as the last gasp of the mission, we sent an empty shell of a spacecraft to impact one of these craters, and we had instruments in orbit and from Earth trying to analyze what was in that plume of material. And sure enough, there's lots of volatile stuff there. Now, there's a lot of other complicated stuff in those measurements, and I'm not going to get into. But again, it really reinforces that there's something going on here at the lunar poles with respect to volatiles. Okay, now what I want to do is help understand how the moon has led us to learn about how the rest of the solar system came to be. So let's start first with Earth-Moon formation. We're talking now about the very earliest time in solar system history, the first few tens of millions of years. And during that time, our initial ball of gas and dust that we call the solar nebula started to spin and contract and organize itself. Now, we theorized, the scientific community, theorized about this for quite some time. And models have been adjusted over time, but it seems to have held up reasonably well. Well, in recent years now, we have deep space observations shown in this bottom panel of this process actually happening around other stars, or at least at the time the light left those things that we're looking at now. And you can see the same kinds of models that we have used, they seem to apply to a lot of these places. You can see this organization being set up in planetary nebulas, solar nebulas elsewhere in our galaxy. So that's pretty exciting. So what we're going to show now is, I talked about this before, the giant impact hypothesis. And let's talk about this for a second. The idea here is that we're talking, again, very early, first few tens of millions of years of the solar system's history. The proto-Earth, we think, was impacted by another object that is about a third the size of that proto-Earth, roughly the size that Mars is today. Now, that's a bad day when you have that kind of cataclysmic event. So what I'm going to show next is an animation, a numerical animation of a model of what we think this might have looked like in a second. And what we're going to see is that after this impact, material is flung out, and there is something that we call the Roche limit, some distance from the center of a planet. Anything that is inside that limit is going to reaccrete onto the planet. Anything outside is free to do its own thing. So we're going to see how that works. All right, here's an animation now of the impactor on the right, proto-Earth on the left, and these the colors of these things correspond to temperature. Again, cooler colors are cool, warmer colors are hot. And check this out. So here's the impact, and what you can see here is total mayhem, total mayhem. The entire world, the entire Earth melts and flings out, vaporizes all of this material. Now the view here is going through the plane of rotation. We're now edge on, and now we're kind of flying around to the other side. So here's the proto-Earth being re-impacted with stuff. There's a big one. And this stuff that's on the outside of the Roche limit is going to start coming together and accrete to form the moon. Now, there's a concept known as potential energy in physics. When you bring a lot of objects all together, they give up a lot of potential energy, and usually that's in the form of heat. And when that happens, it melts the moon as it is coming together, in addition to the moon, or excuse me, to the Earth having melted. We're going to look at this now a little more. This is an animation from the BBC. I apologize that it's very pixelated. That's just the source material, but it's pretty dramatic. It shows this this same process now, visually instead of a mathematical model. And you really get the idea that you don't want to be around when this is happening. Pretty spectacular. So here is the stuff flying around. We're speeding it up a little bit, and here's the moon accreting, sucking up all that stuff, while other stuff rains back down on our poor Earth. Now let's look at this one more way. Whoops. See if this will run. Okay, now, so we have a ball of molten rock. We're starting from that point, and how it's going to start to cool off. This is a great visualization that came out of NASA Goddard Space Flight Center. As it cools off, the crust hardens, thickens, cools off, and you see there's no craters yet. Oh, here comes South Pole Lake and Basin. It was one of the earliest ones. It's the largest one in the solar system. And then a little while later, a couple 100 million years later, more of this accretion that's happening all over the inner solar system is still happening here. And we have this period of basin formation. We call this the late heavy bombardment. Late because it's late compared to the very beginning of Earth history, or excuse me, of Moon history. Long time ago still. These are all these big basins being formed we see on the near side. Now, what you might think is the lava that fills those basins would have immediately come up from these impacts, but that didn't happen, as it turns out. The basins were there for several 100 million years before that influence was felt deep in the interior to get those magmas up to the surface, and that eventually happened. So you're looking here at the era of Mare volcanism. That too eventually cools off, and that activity wanes, and we will eventually end up seeing something that was starting to look pretty familiar. Impact bombardment continues over time, but after that giant peak, it's a little bit less of a, it's not quite as intense, but it is still sustained over a long period of time in the early history of our solar system, the first half of the history, let's say. And then over time, the number of large objects, they're gone, they've been used up, and so that tails off, okay? And it is that whole history of impact that we have been able to tease out with respect to what's going on the moon. Okay, one other thing I just want to touch on this. We mentioned that the moon was a lot closer to Earth in the early history than it is now. Think of a figure skater. When she is spinning, she has her arms close, she's spinning fast, and when she lets her arms go out, she slows down. The exact same thing happens. This is called conservation of angular momentum. As the moon gets further and further from Earth over time, the total amount of spin in the system has to stay the same. And so the only way that can happen is things slow down as the distance gets farther. Now, one of the things that this is kind of like a detective story, like forensics. We understood from the lunar samples that there was this period of bombardment. Well, where did those objects come from? How come they came raining into the inner solar system? Long story short, what we have been able to theorize is that the outer planets, the large, massive outer planets at the top of this diagram, they were actually in a different configuration than they are today. Inside the orbit of Jupiter, we know that we have the asteroid belt, and outside the orbits of the furthest outer planets, we have something we know of as the Kuiper belt, objects that are a source of comets. Well, what we think happened is there were changes in the dynamics of the orbits of these gas giants, and they changed the distances from the sun. And when they did that, they had a big gravitational influence on these asteroids and Kuiper belt objects and flung them into the inner solar system. And that's what caused this late heavy bombardment. There's no way we could have known about this unless we had gone to the moon. You know what else we could have known about if we hadn't gone to the moon is that our own world was completely molten. You saw those models. You saw those images. We've got the data from the samples. Now, because on Earth we have this wonderful thing called plate tectonics, we have a hydrologic cycle that's constantly reshaping the surface of our world. We don't have rocks from way back then that record these geologic events. Rocks are like the pages in the history book of time that we use to study things made out of rock. We don't have any evidence from our own world from way back then. But what we now know is that the consequences of this giant impact actually turned our own world into a ball of molten rock in its earliest history. Now, I don't know about you, but for me, knowing that happened is, I don't know, it's got to be one of the top 3 most important things that's ever happened in the history of our planet. And we would never have known that thing about our own world unless we had left and gone to the moon. So someone asks, why should we bother? This is why. This is how we find our place, is we have to go to these other worlds and understand how they differ from ours and what we learn. So to end this part of the talk, I just want to put up some highlights here that we just talked about and emphasize the point that the moon really is the foundation of planetary science. It really underpins everything we know about rocky bodies, and it also influences what we know about the outer planets as well. The moon is good value. Okay, we're now going to switch gears. We've done the review of the history. We're now going to go into talking about what's coming next, the future. The agency is embarked in a program we call Artemis. Artemis in Greek mythology is the twin sister of the god Apollo, and that makes sense. In Artemis, we will land the first woman and the next man on the lunar surface by 2024. Some of the first steps in that process involve something we call the Commercial Lunar Payload Services Program, CLPS. And I mentioned early on that our return to the moon is not just NASA, not like it was in the 60s. This is a partnership between other international spacefaring organizations like the European Space Agency, the Japanese Space Agency, also commercial entities like these on the screen here, and academics. We need everybody to do this. And this is one of the big differences between now and then is we have this coalition that we're all going back together. It's a sea change. Now we have here's the sort of latest and greatest on the lunar surface right now. We have Chang'e 3 and Chang'e 4 from the People's Republic of China. India recently tried to land on the lunar surface. They came so close before, unfortunately, there was an anomaly and the lander did not make it. The orbiter from that mission, however, is very healthy, doing great science in lunar orbit right now. Israel tried to land a small lander on the lunar surface. They came close. They actually got an image of the moon prior to losing contact with their spacecraft. And then on the right-hand side, the first two vendors that will deliver landers to the lunar surface are shown here. One is called Intuitive Machines. One's called Robotic Technology. Those are expected to fly next year. So we're getting going. Additional vendors that have been chosen are listed here. They're going to be developing more advanced orbiters, landers, and so forth for later in the process. I won't go into the details here. And then on the NASA side, one of the major contributions is this the next big heavy lift rocket called the Space Launch System, SLS, and the Orion crew capsule, which will sit on top of it. And these components will be a big part of how NASA gets its hardware and astronauts up there. Okay, let's now talk about the Artemis program. You're going to see a bunch of these diagrams where I'm going to be adding stuff as time goes on across the surface of the moon here. We're going to be starting off very soon with our CLPS missions and flying some test missions with Orion. The first humans to orbit the moon should fly in a couple of years' time, while more payloads are being delivered to the lunar surface. In particular, something called Viper. You can see there in the middle on the bottom, the Volatiles Investigating Polar Exploration Rover. This will be operating in a South Polar region as a precursor to human landing to try to understand some of the things about the volatiles that we talked about a little while ago. Some of the first support missions will then fly. There will be more infrastructure put down on the lunar surface to prepare for the arrival of humans. And in orbit, we will be developing and flying something we're calling the Gateway. This is a sequence. It's sort of like a mini space station around the moon. Excuse me. And it will help us stage the process of getting to the lunar surface and help us work both in lunar orbit and on the lunar surface. It's in something we call a, get this, near rectilinear halo orbit. It's not just going around the equator. And there's a lot of pluses and minuses to doing that for various things, but I just wanted to include that little detail. Okay, so now let's go back to our swoosh diagram here. Now we have the Gateway in orbit. You can see it there up on the upper right. And as we go along, come 2024, we're going to put our first humans back on the moon. The big difference here is this is not just go plant a flag, walk around, take some samples, and come home. This is building an infrastructure on the lunar surface that will be sustainable, that will be there to stay. The intent of the agency is to go and not leave again to keep us on the lunar surface as a spacefaring species from now on. Eventually, after we establish this infrastructure and ongoing sustainable way of living and working on the lunar surface, we are training ourselves for the eventual journey to Mars. That is the goal we're trying to get to. And when we do these things here in our own neighborhood, just a few days away at the moon, we will learn how to do all the things we're going to need to do when we go to Mars, and do it in a way that, you know, if something does go wrong, we're in a position to help the situation. When you're on the way to Mars, something goes wrong, you don't get to just turn around. There's no gas stations out there either. Okay, so that brings us to the end of my presentation. I want to give you a few takeaway messages here. From our review of the past, we know that studies of lunar samples returned by the astronauts and our really excellent remotely sensed data sets we have now, the navigation and communications work we've done have really set the stage for our return to the moon to take us to that next great giant leap. The partnerships and coalitions that we have established are with international partners, commercial partners, government, academic, and this is something I want everybody to understand from listening to this presentation. We need everyone. We need you. No matter what you do, we don't just need the engineers and the scientists and the astronauts and the technologists. We need human resources professionals, and we need attorneys, and we need bookkeepers, and we need truck drivers and farmers and architects. Everybody. It doesn't matter what path you are taking in your life. There is going to be a time when your road and our road are the same road. So please join us. We're in it for the long haul. This is a return to the moon to stay, and it's the first step on the voyage to Mars. So please come with us. My name is Dave Draper, Deputy Chief Scientist at NASA, and I thank you very much for your attention. I'll be happy to talk in the chat with you and answer some questions. Thanks.